Yes, Assalamu alaikum. Bismillahirrahmanirrahim. In this lecture, we are going to discuss DC to DC converters. That is the bigger category, and we are using these nodes from IIT Kharagpur from India. And this guy is very uh, good in writing some notes. It's a flyback type switch mode power supply, flyback type, and or previously we have discussed forward type forward converter, forward DC to DC converter. Now we will discuss in this is similar to the forward converter with some uh, slight differences. After the completion, we will be able to identify the topology of this converter, and we will explain the principle of this flyback switch mode power supply circuit, and we will be able to calculate the ratings of the device and components used in this, and how to design a simple flyback converter circuit. Introduction. Flyback converter is the most commonly used in switchboard power supply for low output power applications, where the output voltage needs to be isolated from the input main supply. Yes, the output power of the flyback type switch mode power supply vary from few watts to less than 100 watts. That's the beauty of this. This is for the low voltage applications. Overall circuit topology of this converter is considerably very simple. Input to the circuit is generally unregulated DC supply obtained by rectifying the AC voltage and followed by a simple capacitor filter. We will see in a while. The circuit can offer single or multiple isolated output voltages and can operate over a wide range of input variations. We will discuss this also in details. In respect of energy efficiency, flyback is inferior uh, as compared to other topologies, but it is low cost in the low output power range. Commonly used flyback converter requires a single controllable switch, IGBT or MOSFETs, and usually in the frequency range of 100 kHz. A two-switch topology exists that offer better energy efficiency and less voltage stress across the switch, but cost and the complexity of the circuit increases. But we will only discuss the single switch topology over here. Basic topology of the flyback converter. Okay, we will look at the diagram first. This supply DC voltage, unregulated DC. It will be fed to the primary of the transformer with the opposite chart convention, and it is a switch in series with the primary, and in the secondary there is a diode, capacitor and load. And what this explanation shows, we will see. Input to the circuit may be unregulated, derived from the utility supply. We just offered simple uh, filtering. The ripple in the DC output waveform is generally for low frequency, and overall voltage waveform repeat at twice the AC main supply. Yeah, low frequency ripples exist in the DC voltage, and their frequency is twice as the AC mains. But you know that the switch mode power supply usually operates in the range of 100 kHz. In spite of being unregulated, uh, at such a high frequency, this becomes a kind of regulated. How? A fast switching device, sorry, it's here. A fast switching device like MOSFET is used with the fast dynamic control over the duty ratio or duty cycle on off period. to maintain the desired output. The transformer is used as isolation and as well as matching between the input and the output voltage and current requirements. And primary and secondary winding of the transformer are wound to have good coupling so that they are linked by nearly same magnetic flux. As shown in the figure, you can primary and secondary winding of the flyback transformer don't carry current simultaneously, and in this sense flyback transformer works differently from the normal transformer. Usually in the normal transformer under load, primary and secondary winding conduct simultaneously, such that ampere turns of the primary winding is nearly balanced by the opposite ampere turns of the secondary winding. A small difference in ampere turn is required to establish flux in the non-annual course. So the difference is over here, only one winding convert at one time. Only one winding conduct at one time, and it is different than the what it is saying. When this is conducting, look at the diagram. This is positive and this is positive over here, and this is negative. When this one is conducting, this winding cannot conduct. The reason is that this diode is reverse biased when it is conducting, and when the switch is off, okay, and actually we are over here, and let's keep moving. If we see the okay, since the primary and the secondary windings of the flyback transformer don't conduct simultaneously, as I told you, they are more like two magnetically coupled inductor. It may be more appropriate to call the flyback transformer as an inductor transformer. According to magnetic circuit design of flyback transformer, is done like that for an inductor. The result of inductor transformer are dealt with separately somewhere else. Section of this circuit is relatively simple. It consists of the voltage rectification and filtering. This is the filter, the capacitor filter, and this diode is used for the rectification. And the second winding is voltage rectified and filter using a diode and a capacitor. Voltage across this filter capacitor is the switchboard power supply of voltage. It is hereby noted that circuit shown in is a schematic one. A more practical circuit will have a provision for output voltage and current feedbacks and controller for modulating the duty cycle or duty ratio of the switch. This is just a schematic representation. Just if we go for the implementation, we need to control the switch and some other factors like duty cycles. The circuitry is much more complicated. It is more to have. Okay, we are discussing. Yeah, its the complexity will be much more. It is common, usually it is common to have multiple secondary windings for generating multiple isolated voltages. One of the secondary output may be dedicated for estimating the load voltage as well as for supplying the control power to the circuits. Yeah, it's some possible options which are available at the secondary, and there is also a stubborn circuit is required to dissipate the energy stored in the leakage inductance of the primary. There are much more complicated circuitry as compared to this one. When we think about the actual circuit, actually what is the purpose, we just assume, making some simple assumption, we try to understand, and our assumptions are magnetic circuit is assumed to be linear, and coupling between primary and secondary is assumed to be ideal. So circuit explained here is without the leakage inductances, on state losses, and the switching losses, and also core transformer core is also lossless, and input DC supply is assumed to be ripple free. Okay, let's principle of the operation. During its operation, there are different configurations of the circuit. Each of these circuit configuration is referred to as the mode of the circuit, and we will explain in a while how these modes are operating. First one is when switch is on. Look at the bold lines. This is the current where current is flowing. The line is bold. Look at when switch is on, the current is flowing through the primary of the transformer with the dot convention. It's a positive. And uh, on the other side, since the we already know that the dot convention, it takes a plus on the downside, and usually the diode is reverse bias. This is negative, this is positive, and diode is reverse bias, and it cannot conduct. Thus, when switch is on, primary winding is able to carry the current, but current in the secondary winding is blocked due to reverse diode. And the flux established in the transformer core and linking the winding is entirely due to the primary winding current. This is the mode 1 of the circuit operation, which is shown in this figure. So this is all about the ideal situation with no leakage currents and no on-state losses. Under the mode 1, if input supply voltage appear across the primary winding inductance, the primary current rises linearly, and we have a mathematical equation LdI by dt. This is the voltage induced in the inductor. Uh, the DC voltage is LdI by dt, and where L is the inductance of the primary winding and I is the instantaneous current through the primary winding. What will happen next? Linear rise of the primary. Oh, is shown. Flyback circuit may have continuous flux operation or discontinuous. It depends on the it depends. There is two possible options. This is the continuous. This is discontinuous. Uh, how it will be like that? You know, in the case of circuit works in the continuous flux mode, the magnetic flux in the transformer core is not reset to zero because next cyclic timing of the on switch, actually some flux is already present before the S is turned on, switch is turned on. Actually, before, in the previous cycle when this is off and some flow of the current. It is primary winding current abruptly rises to a finite value as the switch is turned on. Magnitude of the current steps correspond to the primary required to maintain the previous flux in the core. Okay, at the end of the switch conduction, the energy stored in the magnetic field of the flyback inductor is equal to L I square by 2. This is the energy stored. V is denote the magnitude of primary current at the conduction end of the conduction. Even though the secondary winding doesn't conduct during this mode, load connected to the output gets uninterrupted current due to the previous charge in the capacitor. During the mode 1, assuming a large capacitor, the secondary winding voltage remains almost constant and equals to this one. Okay, this is a pretty good. The secondary voltage is the term ratio. Mode 1, the dotted end of the secondary winding remains at higher potential than the other end. Under this condition, voltage stress across the diode connected to the winding is the sum of induced voltage in the secondary and the output voltage. So, yeah, you need a high rating diode to protect it from these two, some of these two voltages. Uh, Look at the mode 2 operation of the circuit. Yeah, during the mode 2, which is very interesting, during the mode 2 of the circuit, what you have to do, during the mode 2, when switch is turned off after conducting for some time, the primary winding current path is broken. Now what will happen? According to the law of magnetic induction, voltage polarity across the winding reverses. Okay, and reversal of the voltage polarity makes the diode in the secondary forward bias, and we will show the current path. This is the current path, and so this is a fundamental circuit, equivalent circuit during this mode. Actually, this is off, and we have this kind of situation. Output is V out, and V primary is in mode 2. You already know that though the primary winding is interrupted due to turning of the switch, the secondary winding immediately start conducting. So net MMF, magnetomotive force produced by the winding, doesn't change abruptly. Magnetomotive force that is responsible for the flux production in the core gas is the sum of ampere turns of the two windings. Current entering the dotted end of the winding may be assumed to produce positive, and accordingly current entering the opposite end will produce negative. Continuity of this MMF in magnitude is automatically ensured as sudden change in MMF is not supported by the practical circuit for the reason given below. Okay, the reason is that MMF is proportional to the flux produced, and the flux in turn decides the energy stored in the magnetic field. Energy per unit volume is being equal to V square over 2 mu, being flux per unit area, and mu is the permeability of the medium. Such change in flux means that uh, sudden change in the magnetic field energy. Thus, this in turn will mean infinite magnitude of instantaneous power, something that a practical system cannot support. Yeah, it's pretty important. This MMF is responsible for this kind of phenomena, and you need to understand this in very details. For the idealized circuit considered here, the secondary winding current abruptly rises from 0 to that value, which we have already seen due to the uh, principle of the mutual induction. N1 and N2 are the number of turns, and magnitude and current direction. The second is such that the MMF produced by the two windings doesn't have any abrupt change. The secondary winding current changes the output, charges the output capacitor plus mark, and then the capacitor will have a positive voltage. The output capacitor is sufficiently large such that its voltage doesn't change appreciably in a single switching cycle, but over a period of several cycles, the capacitor voltage build up to a steady state value. And surely, when switch S1 is closed and is conducting, then 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 there is some issue, and then there is certain issues regarding the uh, continuity of the circuit. Steady state magnitude of output capacitor depends on various factors like input DC supply, flyback transformer parameters, switching frequency, switch duty cycle, and load at the output. The capacitor voltage magnitude is stabilized if during each switching cycle the energy output by this equals the energy delivered to the out. Yeah, this paragraph is self-explanatory. Secondary winding currents decays linearly as it flows across the constant output voltage. The linear decay of the secondary current can be expressed as that's the point. Let's where and current respectively. Under the steady state conditions and assumption of zero state voltage drop across the diode, secondary voltage during this mode equals to VO, and under this condition the voltage cross stress across the switch is sum of the total induced EMF in primary and the DC voltage supply. Yes, the secondary voltage in secondary winding while charging the output capacitor starts transmitting magnetic field of the flyback transformer to the power supply output in electrical form. So if the off period of the kept large, the secondary current gets sufficient time to decay to zero and magnetic field energy is completely transferred to the output capacitor and the load. Flux linked by the winding remains zero until the next turn on the switch and circuit is under discontinuous flux mode of operation. Yeah, when you turn off the switch off for a long time, then what will happen? All the energy stored in the inductor goes away. If off period is small, the next turn off takes place before the secondary current decreases to zero, and it is called continuous mode of operation. So it's a very interesting. During the discontinuous mode, after the transfer to the output, the secondary winding EMF as well as current falls to zero, diode in series with the winding stops conducting. The output capacitor will continue to supply voltage to the load, and this part of circuit operation has been referred to as mode 3 of the circuit operation, and it will be shown like that. Even if the everything is gone from this, only the capacitor will be able to support the output. Uh, it may be noted that even if the two windings of the flywheel plant don't conduct simultaneously, they still couple magnetically, and induce voltage across the windings are proportional to number of turns. Okay, this is the primary current, this is the secondary current. You can see that when it is primary is on, secondary is off, and then flux linkage again. Similarly, the primary voltage, and this is induced then in the opposite way. Then this is again mode 1, mode 2. Similarly, is the load voltage. Load voltage is kept constant by the flyback circuits. Okay, here are some other details. Maybe That's enough for the this lecture. We need to just consider